Earlier this year, Microsoft unveiled a new quantum processor that they say will revolutionize computing. The announcement attracted much criticism from the community, but now Microsoft put out a new paper in which they demonstrate some key functionalities. Are they maybe onto something after all? Have we dismissed Microsoft too quickly? Let's have a look. In February this year, Microsoft introduced Majorana 1 that uses topological qubits. According to their press release, they can realize quantum computers capable of solving meaningful industrial-scale problems in years, not decades. If they could do this, that'd be huge. Quantum computers could unlock major progress in several industries, including finance, and that's not just wishful thinking. If Microsoft beats them all by years, they'll get rich beyond belief. Most big companies like Google and IBM have pursued quantum computers with qubits that are superconducting circuits. Microsoft has taken a completely different approach. They want to use topological qubits. The disadvantage of those is that they're very difficult to produce, but the big advantage is that once you have them, they're less susceptible to noise, and that could help scaling them up to larger devices much faster. They want to produce the topological qubits with tiny aluminium wires cooled to about 50 millikelvin. That's colder than outer space, but still warmer than Microsoft's customer service. The press release from February was accompanied by a paper published in Nature that, however, only showed that they could produce one parity state and measure out its two values with 99% reliability. The press release was heavily criticized for overstating the case, as the paper didn't actually show they had any topological qubits. I talked about this in an earlier video. Now, researchers from Microsoft have posted a new preprint on the archive. They say that they successfully created a qubit with 4 Majorana modes and demonstrated that they can reliably read out 2 parity states. So in the February paper they had 2 values of 1 parity state, now they have 2 parity states. This is a key proof of principle, but there are 2 caveats. One is that the error rates for those states are fairly high. In one case 0.5%, in the other 16%. 16%. That's not an error rate, that's a personality trait. The other caveat is that it still doesn't prove that the qubits are truly topological. For that, you'd have to show that they're indeed protected by noise and that they behave as predicted when measurements between the 2 states are iterated. At almost the same time, another new paper appeared that says topological qubits aren't as well protected from noise as everyone thought. The authors claim that researchers have so far underestimated the relevance of 1/f noise, which is ubiquitous in electronic circuits. They say that topological qubits are not well protected from that noise, and it decoheres superpositions within a nanosecond. Well, the guys from Microsoft simply disagree. Chetan Nayak, lead author of the Microsoft papers, told HPC Wire that this problem has been well studied for a decade in theory papers, and we have both direct and indirect experimental measurements in our devices showing that the associated error rates are small. So basically they're saying, whatever the guys in the noise paper calculated, it doesn't agree with what they see in reality. What are we to make of this? Well, neither of these papers have been peer-reviewed. Microsoft has previously had to retract several papers on their topological research, but I think those were honest mistakes. And it's not like anyone actually doubts that topological states exist. They'll get there eventually. But even if that works out, topological qubits are a big gamble, because no one knows how much of an advantage they'll indeed bring. You see, even if they worked as the math says, that'd only protect certain types of operations, so noise will still remain a problem. And meanwhile, other companies are improving their error correction protocols. If I take all this together, it seems to me that Microsoft is still well behind Google and IBM in terms of quantum computing. though they're very competitive in terms of marketing. It's been almost 3 years since ChatGPT's sudden rise to popularity scared everyone into thinking they'll soon be replaced by AI. Today I want to have a look at how things are going and what the future forecasts say. Since our collective attention span is decreasing by the day, let me get my most important message out right away. I think we're underestimating the pace of AI progress, and it's going to hit big in the next several years. It's amazing how quickly everyone has become used to the new reality. You can now generate images, write code, cheat on homework, or launch a startup and go bankrupt all before breakfast. What a time to be alive! If you think people have been overestimating AI progress rather than underestimating it, well, you're thinking of a small but vocal minority. Here's an interesting fact that'll give you something to think about. A study from late last year asked 67 experts how long it'd take large language models to pass certain thresholds of expertise, such as that they outperform virologists on biothreat questions. Their so-called super forecasters collectively estimated that this would happen by 2034. In fact, it happened in early 2025. This means these super forecasters underestimated AI progress by a whopping 10 years, even though they had the tools in front of them. You might say, some forecasters they are. Maybe ultra forecasters would be wrong only by 20 years. I hear you, but my point is that there's a real risk that we're severely underestimating this because we've somehow gotten used to it. A rather scary future scenario came just recently from the AI Future Project, a new non-profit forecasting the future of AI. In a nutshell, they predict that the impact of superhuman AI over the next decade will be enormous, exceeding that of the Industrial Revolution. They have a very specific timeline up to 2027. By mid-2025, we're supposed to see stumbling AI agents, which, well, wasn't hard to predict. They predict that AI training will get even more expensive. That's almost certainly correct. In mid-2026, the Chinese will come and steal all the training results from the Americans. By late 2026, the stock market has gone up 30%. By early 2027, we'll have agents that continuously learn. The Chinese come to steal that as well. And then things really take off. By mid-2027, coding has been fully automated and AI starts to improve itself. In August, the reality of the intelligence explosion hits the White House, presumably while the European Commission is arguing over a regulatory strategy framework for an intelligence tax. In September 2027, AI does all of science, is badly misaligned. By October, everyone's in full panic, and by Halloween, all clocks will strike 10 to 2. Well, that was cheerful. But let's look at some more down-to-earth predictions about the estimated impact of AI on the GDP. The investment firm Goldman Sachs recently noted that AI has surpassed even the previous most optimistic expectations in terms of model use and tech sector investment. While there have not yet been any major impacts on the labor market, they expect that AI will start having a measurable impact on US GDP in 2027, so around the time that the world ends, if you trust the previous prediction. McKinsey likewise reports that the integration of AI into business has been proceeding swiftly in the past 2 years, though for now that's mostly in areas like marketing and sales as well as IT, which makes sense because those are the areas in which we can't tell whether anything's working anyway. The World Economic Forum believes that anything AI, robotics and software development is the biggest productivity contributor for the time to come and will generate a lot of jobs, whereas it's not the right time to start working at a post office. The consulting firm PricewaterhouseCoopers has revised their prediction for the estimated impact on the global GDP. They previously said plus 14% by 2030, now they say plus 15% by 2035. So it seems they were somewhat too over-optimistic. And then we have a guy from MIT who says us that the impact of AI will be non-trivial but modest, which is the academic way of saying, I don't know either, but I don't want to be left out of the discussion. What are we to make of all this? I think the high speed to doom scenarios are unrealistic because they implicitly assume that we'll get to AGI using essentially the same models as we currently use. It seems likely to me instead that companies will have to completely start over again, and I suspect that the intelligent systems will become increasingly fragile and difficult to duplicate. That is to say, I think it'll take more than 2 years, 5 to 10 maybe. But I think that we're indeed at the edge of a remarkable transformation of the world, which, depending on your perspective, is either exciting or terrifying, but either way, a good excuse to have some cheese. One of the reasons I'm on YouTube is to draw attention to ideas you might otherwise never have heard about. In the foundations of physics, it's rare to find genuinely new ideas that aren't obviously wrong, but today I have one that might be going somewhere. It's a recent series of papers from physicists who say that space retains the memory of the matter that passed through it, and that dark matter might be a relic of this memory. That sounds very interesting. Let's have a look. Gravity is special in many regards, and not just because it's refused quantization. One thing that makes gravity special is that it almost seems to duplicate the information from the other forces. Think about it. The gravitational field of a particle contains information about the particle's mass and its momentum. If the particle has an electric charge, that electric field carries energy, and the gravitational field therefore also knows about it. The reverse is not true. The electric field of a particle, for example, carries no information about the particle's mass. To some extent, this duplication is even the case for quantum numbers such as spin and the color charge, though when it comes to those, we run into the problem that we don't have a theory of quantum gravity. Still, I've always found this very intriguing and wondered why there isn't more work on it. There's also gravitational memory, a most remarkable and yet to be confirmed prediction of Einstein's general relativity. When massive bodies such as black holes or neutron stars merge, they emit gravitational waves that stretch and squeeze the fabric of space-time. You'd think that if those waves pass through our planet, they'll wiggle it for a bit and then everything returns to its previous state. But not so. After those waves pass, certain test masses remain permanently displaced. This is known as gravitational memory. Physicists have looked for evidence of this in data from gravitational wave interferometers, but not seen it so far. The new series of publications now isn't directly about either of these memory effects, but it builds on them. The authors imagine space-time as a vast grid of microscopic quantum bits that act as information carriers, atoms of space in some sense. The size of these bits, they say, is at the Planck scale, so they're incredibly small. They call the idea the quantum memory matrix. Sounds like a Netflix reboot. It works like this. Whenever a particle comes by, it interacts with the quantum bits in that location and leaves a memory in them. But in quantum physics, you can't duplicate information. So they say that as time passes, matter gradually loses information to space. One of the benefits of this idea is that it'd do away with the black hole information loss problem. The information never gets destroyed, it's just moved into space. In a recent paper, they go even further and say they can also explain dark matter. That, so their idea, is a consequence of all this information that space is picking up when matter passes through it. That information must carry energy, and so it has weight. And that weight comes out to be just roughly correctly to account for dark matter, or so they say. So what are we to make of this? Sounds good. but I'm highly dubious about this for various reasons. For one thing, where does the extra energy come from that's supposedly in the information that makes up dark matter? Usually dark matter is just assumed to have been produced together with normal matter in the early universe. If you produce it later in some way, memory, effect or whatever, that seems to violate energy conservation. There's also the problem that you can't chop up space into discrete chunks of Planck length size without breaking Einstein's theories. This is because in Einstein's theory, any length, including the Planck length, can get length contracted to a smaller length. So what does it even mean for something to have the size of a Planck length? It means nothing. This is why I give this a 10 out of 10 on the bullshit meter. It's a good idea in principle, but it has a lot of open ends. So why am I telling you about this anyway? Because few ideas are born perfect, and I think this one might have a useful core. Give it some more work and maybe it'll go somewhere. I think one can summarize this idea as space never forgets. So next time you feel like the universe is holding a grudge, maybe it is. A team of physicists has calculated that black holes could form inside of stars and eat them from within. I was fully prepared to dismiss this as nonsense, but after reading the paper, I'm afraid it's kind of plausible. Does this mean that there might be a black hole growing in our sun? Let's have a look. For about a decade, there's been tentative evidence that black holes can have masses below 2.5 solar masses. This is very difficult to explain with the standard mechanism for black hole production, which is a stellar collapse. This is because a star needs to have a certain minimum mass to even form a black hole, so the black hole can't be too small. They could be primordial black holes that have just been there since the beginning of the universe, but that'd be extremely odd, because why would primordial black holes have a mass just about that of normal stars and not any other? That doesn't make any sense. The authors now say that actually this problem was solved decades ago in the early days of dark matter searches, because already back then some physicists pointed out that dark matter particles, under very general circumstances, would accumulate in stars, because, well, stars have a gravitational pull. And one of the key characteristics of dark matter is that it can't build up internal pressure, so it collapses much more easily than normal matter. This indeed is why we need dark matter in the early universe. Without dark matter, the formation of galaxies would be way too slow. This is one of the big plus points of the dark matter hypothesis, that it explains structure formation. If dark matter accumulates in stars, which it plausibly could, then it can collapse in these stars to form a small black hole. This can happen for dark matter particles in the range of 100 GeV or so, as long as they don't self-annihilate. Such dark matter particles are compatible with all other existing bounds. The dark matter would see tiny black holes in stars. They call them parasitic black holes because they then grow by pulling in more and more matter from the star until it collapses. The black hole that's generated that way could have a mass smaller than what's needed for core collapse. In the new paper, they calculate how long this would take for different types of stars. They say that neutron stars, which are as dense as a star can be without being a black hole, can get eaten up very quickly within a few 10,000 years or so. Blink of an eye, cosmologically speaking. For neutron stars that spin very fast, it can take much longer, potentially millions of years. And by then, maybe even I'll have come around to reply to your email. For white dwarfs, which are still atomic matter, not nuclear matter, and therefore have a much lower density, it'd take much longer for the black holes to grow. Indeed, the authors say most of them would never collapse. Rather, the black hole would eat out a polar funnel. That's a hole around the spin axis. The matter that's further outside is protected by the centripetal force, basically. What about stars like our sun? I've good news. they can't grow black holes. You see, black holes decay by Hawking radiation. So if dark matter forms a black hole inside a star, it'll only survive if it eats up matter from the star faster than it can emit matter from Hawking radiation. Normal stars like our Sun just have too low a density for this to work. Also, if this was possible, we'd see stars blink out every once in a while, and no one's ever observed something like this. By the way, this video comes with a quiz that lets you check how much you remember. What are we to make of this? The evidence for small mass black holes is so tentative as to be non-existent. There have been some gravitational wave events where one seems to have been involved, but then again, maybe that was a neutron star. There has been the occasional micro-lensing observation with suspiciously small masses, but for one thing, the error bars are large, and again, maybe it was just a neutron star. So basically, there's no evidence backing up this idea. Still, I don't think it's complete nonsense. On the bullshit meter, I give it an 8 out of 10, which for dark matter research is pretty good. This is because it works with fairly general types of dark matter particles and doesn't require all that many parameters to fit together. And the idea that dark matter sneaks into stars, collapses them, and eats them from the inside is also a pretty good metaphor for modern academia. Thanks for watching. See you tomorrow.